Hello, my name is Nur Ahmed. Today in this video, I would like to create a PWM generation in VHDL and also generate a dead time from this PWM signal. So my background is actually analog and the mixed signal IC design, but I'm doing research on the FPGA too. So I'm also new to hardware description language. I searched online about the PWM generation and the dead time generation. I couldn't find there are a lot of tutorials there, but I couldn't find one that needs my specifics, especially the dead time generation. So in this video, I choose the simplest way. So I did my uh, research. I learned about the VHDL in the past week, and then I created these two different blocks, PWM generation and the dead time generation myself. So hopefully this video helpful. So this video may be a little bit long, so I would like to divide this into two parts. The first part is PWM generation block. In the next video, we're going to generate the dead time generation. And also we do some simulation on the Vivado. So for the PWM generation, the method is the simple. We have this counter in the FPGA, so it's gonna count from 0 to until the maximum value, then it's gonna reset and then count again. So we have this duty cycle, duty ratio, compare with this counting. Whenever the duty is bigger than this carrier signal, then our PWM signal will be high. And then here it will gonna be low until up to the reset the counter. Again, here the duty is bigger than carrier signal, so it's gonna go up, and then here go down until this point, and then again if the duty cycle changed, right? So here again the duty is bigger than carrier signal, but for a little bit longer time. So it's gonna change the duty cycle, until this point. And then for the this period, we're gonna, in the small period or small amount of time, it's gonna stay low. So we're going to write this in VHDL in Vivado. Let's start create video. So I'm gonna name this as PWM gen in this folder. We're gonna use RTL, create file, name it as PWM gen. Okay. So the target language is VHDL, but the simulator I would like to use the Verilog. So I just choose as a mixed. Next, we don't need constraint now. So I'm targeting RTX 7 FPGA architecture. This would work for any FPGA. So architecture behavior, our port name, we have some in this block we have clock signal. I would like to have reset, and another one is the PWM output. So I'm gonna name it PWM over gen and out. This is direction as output, and okay. So in the library file, I'm gonna use numeric because we are going to add some calculations. So it's gonna numeric all, and also add this logic, sending logic, and unsigned. Now, because there's a comparison, I don't know why. If I don't include this library, then there will be some syntax error. So if you know about this, please let me know in the comment section. I'm not much familiar with this library thing. So we have entity, clock, reset, PWM gen out as our output, and in the architecture, I would like to here define a few parameters. Like our duty is it's gonna real number because it's a decimal number. So let's start with maybe 0.6. We're gonna change our duty ratio later according to the PWM signal. And also we have the clock signal. We can choose as an integer. Let's say our clock signal is 200 meg. 200 meg. That's our clock frequency. And our PWM signal, the switching frequency of PWM signal, let's choose as, let's say, 400 kilohertz. And then what else? Also we have counter, right? Before that, yeah, we have a counter. It's gonna counter. This is the counter for the PWM as a vector. So it should counter until what value? So we have clock frequency of 200 meg and our switching frequency is 400. So in one switching period, it should count until up to F clock divided by switch, which is 500. So 200 meg divided by 400 kilohertz, that's gonna 500. So in one switching period, there's 500 counting. So how many bits should be our counter? Let's see next power of 2 of 500 is 9. So 9 bit, the smallest bit should be 9 bit. So here it down to 0 because it starts from 0. So 9 bit is enough for the counter. And another thing, the counter should be compared with the duty ratio. Duty ratio is 0.6, but we're gonna convert this duty ratio to the counting so that we can compare with the counter. It's gonna signal. Let's name this duty count. It's gonna be integer. And so that's gonna be calculated by our duty multiplied by so in one switching period there's 500 counting, right? So we're gonna use this F clock divided by F switch. So later on, if we would like to change these values, then we don't need to change this duty count. So that is our duty count. So then our counter will be compared with this signal duty count. Now, since here the real number multiplied by the integer, so we would like to convert this signal to integer type. Alright, so we defined the parameters. Now start process. Sensitivity list is clock. Begin. Now we have reset signal. So if reset signal is equal to 1, So that's gonna active high. Then we're gonna reset the counter. So the counter's values, all of them should be 0. Else if reset is not 0, is not 1, then in every rising edge of clock, first we're gonna define in terms of the counting. So still this counter doesn't know count until which number, where. So it's gonna count until here or here, right? So we have one switching period, 500 values, right? So if the counter start from 0 until count up to this value, then it's gonna reset. So in rising edge of clock, now if the counter PWM is smaller than, so we again use this F clock divided by F switch, so it's gonna 500. Since it's starting from 0, the counting, so we're gonna -1 subtract 1. So the counter is still smaller than this value, then we're gonna continue to count. Else, if it count up to that 500 value, right, 500 counting, then the counter should be reset to 0. So here we define it in one switching period. The counter should be count up to until up to this value. If count up to this value, then we're going to reset the counter. So here, and if we have also for if here, so that's gonna end if there, and then we're gonna end the process. Now we defined the switching period. Now we define the duty. So when it should be high PWM signal. So the counter, so counter count until up to duty ratio, this duty count. If it is smaller than duty count, then PWM signal should be high. Otherwise, it's going to be low. So here, our output PWM gen out should be 1 when the counter smaller than duty count. Else, it should be 0. So I hope it's clear. Now we have Snytax error here. What is this? Missing. Is that a column? Did I miss some column here?
A few moments later.
I don't get it. Where is the mistake? 25. Huh? Syntax error 10, 25. 25, which is this line. Else. Oh, else if.
A few moments later.
Whew. It was else if. What did I write? I think I write it anyway. Else if writing like this. I didn't know that. Else if. So there's a syntax error. This else if should be spelled like this. If reset is 1, the counter should be 0. Else if rising edge clock, then we're gonna define one switching period. If it is smaller than this value, then the counter continue to count. Otherwise, it's gonna be 0. And then here, if the counting smaller than this duty ratio, then PWM output logic high. Otherwise, it's gonna be 0. All right. So we're gonna simulate this one. Let's create just simple simulation file in Verilog. That's gonna be let's say PWM gen Testbench. I would like to create it in Verilog. Finish. PWM gen Testbench. So here we have 200 meg. That means our clock frequency, the period is 5 nanosecond. So time unity here, choose 1 nanosecond is good. And module, we don't have ports here. So module PWM gen Testbench. We're gonna define some internal signals. So register, we have clock, and then we have reset register. And for the output, we just define as a wire. So PWM gen, that's gonna be out. And so our PWM gen, that is device under test. That's gonna take these pins. PWM gen out. That's gonna take these pins. Syntax error here. I think there's a column. I think there's a column here. Right. And then so initial begin the simulation. Clock starting from 0. And then our reset signal, at first it's gonna start with 1. After some 500 units, then we reset the signal to 0 and end. And finally we have the clock signal. So 5 nanosecond switching period. That means in every half of the switching period, because the clock is 50% duty cycle. So in every 2.5 time unit, the clock should be flipped. Right? So that is our test bench. Here, PWM gen is our device under test. Let's run simulation, have a look. Okay, so we have this clock signal here. Reset signal first starts 1 and then the 0. Let's run 10 microsecond for another 10 microsecond. Zoom fit. All right, so here then PWM signal is generated here. From here the reset signal starts from 1. When it's 0, the reset signal if reset signal keeps at 1, then the counter should be set to 0. Okay, so the counter until as long as the reset is logic high, then the counter keeps at 0, and then once it's released, then PWM count starts from at this point. Then it's gonna count until this duty count, PWM high and then low, PWM high and then low. Let's change our duty ratio here. Let's make it a bigger. Let's say 0.85. Then this relaunch the simulation. Let's run for another 10 microsecond. Let's have a look. So yeah, here the duty ratio is changed to 0.8. So as you can see here, PWM also synchronized to this clock. Let's change to smaller value. Let's say 0.2. Simulation. Okay, so the PWM duty cycle changed to 0.2. Alright, so this is PWM generation in VHDL and the simulation. In the next video, we are going to generate complementary PWM signals with that time. Thanks for watching. See you in the next video.